Hi everyone, a very good evening. I hope I'm audible and visible. Can you guys see me? Can you guys hear me? So, we are on with another session on reading comprehension for MA at CT, and we'll be practicing some social science passages today. Okay, so let me bring down a good passage for you. So, this is the first paragraph we have. Please have a look at the paragraph. There are just three paragraphs to it. Once you're done with this one, I'll take you to the next slide. Giving you 20 seconds, quickly go through the paragraph and then we discuss what is there in the passage. Please let me know if you're done reading. We'll move ahead to the next slide. All right, guys, we'll move ahead to the next slide. Quick 20 seconds and then we discuss this. All right, let's move to the next slide. It's the last paragraph, and then we discuss the question. Okay, let's go through the passage together and see if the understanding is on the same page. Both of us, like you guys and we here, are able to comprehend the same line of thought given the passage. So this passage is about public transportation system that was there in urban areas. We're talking about the design. So design of public transportation systems in urban areas often reflects a distance that is between accessibility and efficiency. Okay, so what is the main point of discussion here? We're talking about the architecture of public transportation system. Okay, so it compares urban areas often reflects the balance between accessibility and efficiency, like how accessible our place of work could be, our homes could be from place of work. Efficiency in terms of how efficient, how easy is it to reach that particular place. So, for example, in densely populated cities, subway networks tend to have a higher number of stations per mile of track compared to less populated cities. Okay, so here it's talking about subway networks tend to have a higher number of stations, right? Whenever we have subways as in the road, crossings that is underground. Whenever we have these subways, we find that there are more number of stations compared to less populated cities. However, the growth in number of stations is not proportional to the population size. So if we have more number of subway stations or more number of stations for a metro or anything, or for that bus particularly if we talk about on road, it doesn't anyway proportionate the population size. We can have more number of stations, we can still have lesser population in a certain city or a country. So instead, researchers have observed that larger cities often optimize the transportation networks by concentrating stations in areas of highest demand, leaving lower density regions with fewer stops. Results in scaling relationship where the number of stations grows at a slower rate than the population. So what we're talking about is we're talking about relationship which can be scaled where number of stations are more. Stations grows at a slower rate than the population itself. A similar pattern can be observed in biological neural networks in the brains of mammals. The number of neurons increases with brain size. So if we have a larger brain size, that will have more number of neurons. But the number of concentrations or the connections per neuron, it decreases in larger brains, right? So if we talk about the connections in larger brains, it would have lesser number of connections, but more number of neurons. So this phenomena known as neural scaling allows larger brains to process information more efficiently without the prohibitive energy costs of maintaining an exponentially growing number of connections, right? So this entire phenomena we're talking about neural scaling, it allows larger brains to process information efficiently without the prohibitive energy of maintaining an exponentially growing number of connections. So one thing is I have to manage many number of many connections, my friends network, my relatives network, or maybe many projects in my organization, right? So maintaining those large number of connections, it says it is without the brain actually needing any neural scaling for it. So this scaling we're talking about here is neural scaling. It allows larger brains to process information more efficiently without using any extra energy for these new connections which are being built up. So, for example, while a mouse brain is densely interconnected, an elephant's brain compensates for its vast size by having fewer connections per neuron. Right? So that neuron would not be connected to many other neurons if it's a brain size which is larger than expected. Okay. And then it says systems scientist Deborah Gordon has suggested that such scaling reflects a universal principle of network optimization. Whether in urban transit systems or neural networks, the goal is to balance the benefits of connectivity with the constraints of energy, space, and time. These trade offs shape the efficiency of systems across vastly different contexts. Okay, so the entire thing we're talking about is how the neurons are connected, right? How the neurons are connected, the connectivity between the neurons. And then we're talking about the Deborah Gordon has suggested that such scaling reflects a universal principle of network optimization. Whether in urban transit system or neural networks, the goal is to balance the benefits of connectivity with the constraints of energy, space, and time. And these trade offs shape the efficiency of systems across vastly different contexts. Okay, so I hope the entire passage is clear to us. Can we quickly calculate the general idea, the structure, and tone, guys? Please help me with the GST of the passage before we move to the questions. Giving you a quick 2 minutes. I'll also circulate through different paragraphs in case you want me to. But we move to questions only once we know what is the general idea, structure of the passage, and the tone of the author. By structure, it's the functionality of the passage. Guys, can we quickly discuss? What is the general idea about? The passage starts with an architecture for public transportation, the connectivity, the network of transportation system, and then slowly and gradually move towards the densely populated cities, subway networks coming out of it, growth in the number of stations, which is said to be not so proportional to the population size. Instead, researchers have observed that larger cities they have rather better network. They've often optimized the transportation network by concentrating stations in areas of highest demand. Wherever we find that most crowd, steps in from, so they would have a station there. Leaving lower density regions with fewer stops. Of course, when you know that there is less density as compared to other areas, we shall keep that areas. We should not keep a station there. So this results in a scaling relationship where the number of stations grows at a slower rate than the population. So we're talking about scaling here, like how the number of stations can grow as per the density. And then he is trying to connect to the same thing with a similar pattern that can be observed in biological neural networks. In the brains of mammals, the number of neurons increases with brain size, but the number of connections per neuron decreases in large brains. And this phenomenon is neural scaling, right? And then finally, he comes up with an example which Debruha Gordon also stated, that such scaling reflects a universal principle of network optimization. Whether in urban transit systems or in neural networks, the goal is to balance the benefits of connectivity with the constraints of energy, space, and time. And these trade-offs shape the efficiency of systems. Like how efficient the system is going to be, it depends on the trade-off altogether. Now, guys, I'm going to show you the questions. We've discussed the general idea. Tone, of course, is a bit analytical. He's trying to draw a parallelism between the neural networks and road networks. Okay, this is a primary purpose question. I'm giving you quick 2 minutes. Understand the question stem well, go through the options, eliminate the options, and then if you feel like going to the passage, let me know. Quick 1.5 minute, guys, not more than that. Okay, so what is the question about? It's the primary purpose of the passage. Is it to describe a principle that explains patterns observed in various systems, or to argue for the accepted applicability of a specific scientific theory of diverse contexts, examine differences in the structures of natural and human-made systems, or is it illustrating a biological phenomena by comparing examples in different domains, or suggest that efficiency is a defining feature of complex system? Since it's a primary purpose question, I'm letting you quickly have a look to the first paragraph, and then if you're able to figure out the answer, good enough. If not, I'm anyway going to support you with the correct answer. Okay, so let's go back to the question. Tell me, guys, what is the answer? I see only a few answers so far. More to come in the chat box, guys. Please comment here. Describe a principle that explains patterns observed in various systems. Are we just describing patterns on the basis of some observation? Or is it arguing for the applicability of a specific scientific theory to diverse contexts? Are we trying to relate to a theory and that too in different contexts? Could be. Examine differences in the structures of natural and human-made systems. Illustrate a biological phenomena by comparing examples from different domains, or suggest that efficiency is a defining feature of complex systems. So we look at option number B, argue for the applicability of a specific theory to diverse context. So not necessarily an argument, but yes, that is what we majorly see. We're talking about observations here, right? And then it says that argue, of course, is not a good option. Examine differences in the structure of natural and human-made systems. Illustrate a biological phenomena by comparing examples from different domains. I think it could be D rather than going for B, because there's no argument as such. In option number B, we are talking about argue for the applicability of specific scientific theory, but the author doesn't really argue. Okay. Illustrate a biological phenomena by comparing examples from different domains. Yes. We see the neural connectivity has been compared here, right? So D option is the correct answer, guys. I hope everybody answered it correctly. In case not, I hope you know the answer now. Okay, let's move to the next question. Please have a look at this one. What is the purpose of using discussion of natural scaling in mammals? Now, why are we referring to natural scaling in mammals in the passage? So it's a specific question. It's a local question that comes from a specific part of the passage. Let me know if you're done reading. I'll take you back to the paragraph to just refer once very quickly. Okay, let's move back to the paragraph once. Quickly refer this. All right. So, primary purpose of the passage discussion of neural scaling in mammals is to what? Provide an example to demonstrate the energy trade-offs inherent in biological systems. So here it says similar pattern can be observed in biological neural networks in the brains of mammals. The number of neurons increases with brain size, but the number of connections per neuron, it does not, right? In large brains, the number of connections per neurons decreases in large brains. Okay, and this phenomena is known as neural scaling. This is what it says as neural scaling. Now, if we look at this statement which is given here about neural scaling, and we look at the question is about what is neural scaling's reference. Is it providing an example to demonstrate the energy trade-offs inherent in biological systems? Providing an example to demonstrate energy trade-offs. Extend the concept of network optimization to include the structural features of urban systems. Illustrate a general principle regarding the relationship between network complexity and size. Support a claim about the differences between natural and human made networks, or suggest that neural networks are more efficient than any other types of networks. What do you think is the paragraph doing? Is it option number B? Is it option number C? Illustrate a given general principle regarding the relationship between network complexity and size. Are we kind of giving any examples stating that natural networks are more efficient than other types of networks? Not really, right? But support our claim about the difference between natural and human made networks. So we're trying to draw a relationship here, right? And we're supporting a claim. So answer should be D, Delhi, for this particular question. Okay, last question for this paragraph. This is a critical reasoning question, strongly supported by the information in the passage. Please have a look at the question and then we discuss it together. All right. Which of the following is most strongly supported by the information in the passage? Larger cities require fewer transportation connections per capita compared to smaller cities. Are we talking about the connections here? Or is it in mammals, the total number of connections per neuron decreases as the brain size increases? The number of neurons in the brain increases in proportion to the size of mammal, but the number of connections per neuron decreases. Neural scaling in mammals primarily driven by the energy needs of individual neurons. Efficiency in complex systems is achieved by maximizing the number of connections per unit of size. Okay, so what are we talking about in the statement? We're talking about strongly supporting the information in the passage. Okay, so what is the information in the passage is very important. What am I trying to support? What is the conclusion we are trying to support? Right. So overall gist of the passage is something we've already also decided in the first question. It was about examining the differences in structures of, illustrating a biological phenomenon by comparing examples from different domains. Right. Now, if I have to strengthen this entire conclusion, is it efficiency in complex systems is achieving by maximizing the number of connections per unit of size? Is it neural scaling in mammals is primarily driven by energy needs of individual neurons? Or number of neurons in the brain increases in proportion to the size of the mammal, but number of connections per neuron decreases? Don't you think? It gives you an example of an elephant, right? Here in the last sentence of the paragraph, while a mouse brain is densely interconnected, an elephant's brain compensates for its various vast size by fewer connections per neuron. Okay, so now if you look at option number C, number of neurons in the brain increases in proportion to the size of the mammal, but the number of connections per neuron decreases. Don't you think this supports the information given in the passage? So answer should be option number C for this question, right? For this, we just had 3 questions. Let's move to another passage now. Okay, this is a little lengthier passage, guys, and then we have some good questions. Please have a look at it, then we discuss this. Please let me know if you're done. We'll move ahead to the next slide. Okay, please have a look at the next slide now. Please let me know if you're done. ठीक है, let's move to the next. Okay, guys, I think We are good to move to the next one. Please have a look at the next slide. Okay, there's a paragraph and then we have the questions. Quickly have a look at this, 30 seconds. Guys, can we discuss it now? I think not a very tough passage. So it starts with a contradiction. It says, despite the bilateral nature of human auditory system, many species, including humans, exhibit lateralized auditory processing. Certain birds, such as zebra finches, favor their right ear when listening for predators. Right. So there's something with the, auditory system. Auditory as in like what they're listening and which ear do they prefer, which side. So, for example, let's talk about the zebra finches, which uses its right ear to know about the predator's presence. While frogs often respond more to sounds entering their left ear during mating calls. So in humans, this asymmetry is most evident in speech processing, which typically engages the left hemisphere. So it's like which side of the part of the body is more engaged in certain situations. Less apparent, however, is a tendency to react more quickly to sounds entering the right ear. Studies indicate that people prefer to hold phones on their right ear despite equal hearing capacity in both, suggesting a deep neural basis for this phenomena. So basically, what are we trying to do? We are trying to see what works the best as per the body parts and situations, right? For example, we humans, we are more, inclined towards holding anything towards the right? Because of course we are all rightist that way, not lefty that way, but still we like to hold things by right. We like to hold our phones to the right ear because though both the ears can equally hold it well, here the hearing capacity is equal in both the sides, both the ears, but still we prefer right ear over left. So this is general tendency, right? Which suggests a deeper neural basis for this phenomenon, that it's not something which is happening on its own. It has to do with the rationality behind it. So the rationality is the neural basis for this phenomenon. Next paragraph should, of course, talk in deeper context of neural basis. What exactly is it? It says Kimura found that individuals asked to recall digits were more accurate when the numbers are presented to their right ear. Because they heard it from the right ear, there was chance that they focused more while they listened to the digits. And when they heard the digits, they captured the numbers more. So Kimura found that individuals asked to recall digits were more accurate when the numbers are presented to the right ear. She suggested that this bias reflected the dominance of the left hemisphere in language processing. However, subsequent research by Biden proposed that environmental factors such as handedness might contribute to ear preference. Despite this, later studies confirmed that right ear average advantage persisted even when such external factors were controlled, reinforcing the role of hemispheric specialization in auditory tasks and cognitive processing. So, one is auditory task, that is what we are hearing, what we are listening from which side of the ear, and the other one is cognitive processing, which is very important. How are we taking the information we're getting and how we're processing it and reacting to it, right? So Kimura found that individuals asked to recall digits were more accurate when the numbers are presented to the right ear, suggested that this bias reflected the dominance of left hemisphere in processing language processing. However, subsequent research by Brighton proposed that environmental factors such as handedness, right-handedness or left-handedness, that's what it's referring to, might contribute to ear preference, right? That's what we were discussing. That if somebody is lefty, he would prefer to hear from the left side. If somebody is righty, he or she would prefer the right ear advantage, right? So despite this, later studies confirmed that the right ear advantage persisted even when such external factors were controlled. Still, people were more inclined towards using the right ear. So then they concluded that it's both the things. It's just not auditory task, but also cognitive processing as well. Dosh explored whether this lateralization extended to musical perception. In her study, participants listened to melodies through headphones and were tasked with identifying pitch variations. Right-handed participants consistently performed better with the melodies were presented to the right ear. Dosh hypothesized that this was due to the left hemisphere's superior processing of temporal patterns, essential for rhythm and melody recognition, particularly for complex compositions of unfamiliar pieces requiring greater auditory attention. So then, everywhere you find that it's giving you some, statements from some or the other researcher. Like Kimura found that individuals asked to. He was also researching on which side people prefer to listen to more, right side or left side. Then we have Dosh explored whether this lateralization extended to musical perception. Is it just about the numbers, recognition of the numbers or questions being asked, or is it also about the musical perception? In her study, participants listened to melodies through headphones and were tasked with identifying pitch variations. So, what sort of pitch was it? They were asked to figure out what pitch variation was it coming from. So, right-handed participants consistently performed better when the melodies were presented to the right ear. Dosh hypothesized, now on the basis of this, the theory she came up with was that this was due to the left hemisphere's superior processing of temporal patterns, essential for rhythm and melody recognition, particularly for complex compositions or unfamiliar pieces requiring greater auditory attention. Okay, so this is not just about, not just about auditory attention, but there could be some other things as well. So to check that, whether it was also the cognitive presence, which was impacting the mammals, impacting humans, impacting which side is it? Because the passage, if you see, it started with birds, then it came to frogs, and now we're talking about humans, how humans can also get swayed. Okay, so right-handed participants consistently performed better than the melodies were presented to the right ear. Dosh, on the basis of this, hypothesized that this was due to the left hemisphere's superior processing of temporal patterns, which is essential for rhythm and melody recognition, and particularly for complex compositions or unfamiliar pieces requiring greater auditory attention. Okay, now can you relate to this paragraph, guys? Not all studies align. Beck suggested that ear preferences might stem from the mechanisms of the auditory pathway rather than neural dominance. This experiments proposed participants to speech and non-verbal sounds in soundproof environments. Beck found that while speech favored the right ear, non-verbal stimuli showed no significant ear preference, suggesting differences in how the brain organizes auditory inputs. Right? Then it's talking about that somebody said something, X said something, Y said something. And on the basis of all of this, it says not all studies align, but not all the studies align. Beck suggested that ear preferences might stem from the mechanics of the auditory pathway, right? Which preference do we have? Is it the left side or the right side? That might depend, you know, that might stem from the mechanics of auditory pathway rather than neural dominance. It's not the neurons which are impacting it, but it's basically the listening capacity and the canal, the auditory pathway, which is dominating here. His experiments exposed participants to speech and non-verbal sounds in soundproof environments. Beck found that while speech favored the right ear, non-verbal stimuli showed no significant ear preference. So if it is the verbal communication, maybe they were favoring the right ear. But if it was any kind of non-verbal stimuli, non-verbal communication that was happening, it showed no significant ear preference. It just suggested differences in how the brain organizes auditory inputs. Okay, quickly tell me, how does this paragraph add to the conclusion? Since it's the last paragraph, can you help me in understanding how is this as a conclusion here? Giving you 1 quick minute, guys. Please drop in the chat box and then we discuss this. Let's have a look at it. It says to build on this, Beck tested sound localization. What are we doing? We are going through different tests. The paragraph started with auditory preference, right? It started with how auditory processing happens. And it gave some examples of birds, frogs, and then eventually humans. Then we had how the other volunteers were tested upon their listening, their hearing tendencies, right? So we got to see from Kimura's references that the students, the pupils she might have studied, she suggested that this bias reflected the dominance of the left hemisphere in language processing. That if people wanted to use their right ear to listen to the numbers that were being fed, they wanted to use the right ear. However, subsequent research by Bryden proposed that environmental factors could be contributing. Then we have Dosh, who explored whether this lateralization extended to musical perception as well. And then she hypothesized that this was due to left hemisphere superior processing. And last of all, it says not all studies align. Beck suggested that ear preference might stem from the mechanics of auditory pathway. Beck found that speech favored the right ear, non-verbal communication stimuli showed no significant ear preference. And to build on this, Beck also tested sound localization under varying noise conditions. His findings reveal that noisy environments, individuals consistently relied on their right ear regardless of sound type. This suggests that ear preference, while linked to hemispheric specialization, may also reflect situational adaptations, highlighting complexity and variability of auditory lateralization. Okay, so this is what we have figured out so far. The tone is about analysis. We are using different references just to come to conclusion that it's not just the auditory lateralization, but it could be more than that, right? And everybody's viewpoints have been considered here. We have good 4 paragraphs, 4 questions to cover, guys. 10 minutes. Let's quickly have a look at the first question. I'm giving you 2 minutes. Let me know once done. Or if you want to move back to the passage, I'll take you back to the passage since it is a specific question. It says, which of the following statements concerning the studies of Kimura and Dosh most accurately reflects information provided in the passage? So please have a look at the paragraph in case you want to. I'll take you back and then we discuss it. Okay. It says, which of the following statements concerning the studies of Kimura and Dosh most accurately reflects the information provided in the passage? Is it like both of them concluding that the right hemisphere is more effective in processing nonverbal sounds? Kimura's study demonstrated that handedness plays a critical role in auditory recall, while Dosh's study found that musical perception favors the right ear. Each study highlights a different aspect of auditory lateralization, Kimura focusing on speech recall and Dosh on musical perception. Both researchers agree nonverbal are processed exclusively by the right hemisphere, regardless of the environmental factors, or is it Kimura and Dosh's findings primarily challenging the notion that lateralization affects complex auditory tasks? So you can have a comparison here, guys. The second paragraph and the third paragraph. Tell me what is the answer. So as per Kimura, she did feel that right here, people were more alert when it comes to feeding the numbers to the right ear, right? Whereas, as per Dosh, explored the lateralization extended to musical perception as well. And on the basis of this, she hypothesized that this was due to the left hemisphere superior processing of temporal patterns. So now, if we look at B, Kimura's study demonstrated that handedness plays a critical role in auditory recall, while Dosh's study found that musical perception favors the right ear. Isn't B a better choice here? Okay, let's have a look at the next question about Beck's study. Quick 1 minute. Okay, so strongly supported by the findings of Beck's study. Quickly going through the options, auditory recall improves when participants are exposed to verbal stimuli through the right ear, even if they are left-handed. In quiet environments, non-verbal sounds are processed equally by both hemispheres, leading to no significant ear preference. C says complexity of sound rather than classification, as speech or non-verbal determines which hemisphere processes the auditory input. Or D, which says participants consistently favor their right for speech in noisy environments, but only when non-verbal stimuli are also present simultaneously. E talks about individuals tend to rely more on their right ear for verbal stimuli in noisy environments, regardless of handedness. So tell me, guys, what's the answer? Is it B, Bombay? We're talking about Beck's study. Let me take you back to what Beck said. Beck suggested that ear preference might stem from their auditory pathway rather than neural dominance. Okay. And then it says his experiments exposed participants to speech and non-verbal sounds in soundproof environments. Beck found that while speech favored the right ear, non-verbal stimuli showed no significant ear preference. To build this, she also tested localization under various noise conditions, suggesting that ear preference, while linked to hemispherical specialization, reflected situational adaptations. Okay, so now please let me know the right answer. Is it C, complexity of sound rather than its classification as speech or verbal, non-verbal, it determines hemispheres? Isn't it? C, the best choice. B says quiet environments, non-verbal. We don't know about what happens in quiet environments. Rather, she did focus on noisy environments, right? So C, Calcutta is the correct answer. So similar to the session we had today, guys, we'll be having more MAH CET RC sessions and also some verbal ability part as well, wherein we'll be covering some grammar, some of your critical reasoning questions, and also touching base on para jumbles, para completion question types as well. Also, MHCT is very fond of throwing some really lofty words when it comes to vocabulary. So make sure that when we read the passages, we're also working on the vocabulary alongside. All right. So we'll be keeping the session till here, guys. Thank you so very much for joining in. We'll catch up very soon for the next session. Thank you so much.